Mohamed Hibat-Allah, he did his PhD at University of Waterloo, and he was working at Zapata for a while with some people, and he will be talking about a project that he did there. And currently, he's a PSI fellow and at Perimeter Institute. And in this talk, Mohammed is going to talk about comparing generalization of quantum and classical generative models towards practical quantum advantage. So thanks, Mohammed, for accepting our invitation. And please start. The stage is yours.
Yeah, thank you so much for your kind words and for the very kind invitation. It's actually my pleasure to be here. So today it's my immense pleasure to speak to you today about the work that has been conducted during my internship at Zapata Computing, where we tried to do a generalization comparison between classical and quantum generative models as a way to search for a practical quantum advantage. So first of all, I would like to acknowledge all my collaborators without whom I wouldn't be able to show you the results that I'm going to present today. So I would like to thank Marta, Juan, Alejandro, and Caitlin for being amazing collaborators. And I would like also to mention that this presentation will include material from 2 research papers. So the first one will talk about how we can assess, that will show that quantum machines can actually generalize. And in this paper, we'll focus on how we can compare generalization both in classical and quantum generative models. So first of all, I think a good start in this presentation would be to define what would be a practical quantum advantage. So, of course, if you look into the literature, you'll find that it's a very ambiguous, it's lots of definitions. But one way we could define what's a practical quantum advantage is the ability of a certain quantum algorithm to perform a useful task either faster or better than some other classical algorithms. And in our research, we focused on the task of generative modeling as a way to search for practical quantum advantage. And the way we did it is through the analogy of setting up a race between quantum and classical quantum advantage. So the analogy here is that you can think of generative models as different racers. So you can think of the quantum generative model as this racer over here that has strengths and weaknesses. And also you can think of a classical generative model as a racer that has also different strengths and weaknesses. And you can imagine putting these racers into a race that has different hurdles. So, in generative modeling, we have a lot of hurdles. So examples of those hurdles are training hurdles. We also have sampling hurdles. And also we have expressive power hurdles. And the idea is that if we have different hurdles, and if you imagine that we have different tracks, so for instance, as noted over here, we have track 1 or track 2. So if you have, for instance, a longer track or a shorter track, or let's say, for instance, you have different types of grams, so either you have solid or a grass, then you'll expect to get different results based on the strengths and weaknesses of each generative model. So this was the main idea that we try to focus on in this paper. So we're kind of establishing a race between different competitors, and the competitors are the generative models. And as I mentioned here, the criterion we use to assess who is the winner in the race is the generalization, where the goal is to generate new and good samples based on some training data. For instance, if we use this set of images as a training data, we hope to get some new images that are new and also good looking. And to define what's good here, and I'm going to show you in the next parts how this can be done through a set of generalization metrics. And it turns out in this work, we have shown that this generalization is actually a prominent candidate for practical quantum advantage. So to get started, the plan for this presentation will be as follows. So in the first part, I'm going to show you how we can assess generalization, and I'm going to show you how we can show that quantum circuit-borne machines can generalize. And in the second part, I'm going to show you how we can set up a race between classical and quantum generative models. Now, before moving to the first part, are there any questions so far? So far, so good?
Yeah, I mean, okay with me. Yeah. If
Sounds
others
good.
have any question, please interrupt and ask.
For sure. Yeah. If you have any questions, yeah, for sure, feel free to interrupt me. So now let's get started with the first part on the generalization of quantum circuit-borne machines. So as you might know already, like quantum circuit-borne machines are quantum generative models, where the idea is that you have some initial set of qubits where you apply some unitary. So this unitary can have many forms. So for instance, if you take what's called the line topology, you will have a unitary that looks like that. So initially you have a set of single rotations, and then you apply sets of 2 qubits gates. For instance, here we have the XX gates, and what we do is we can repeat these set of these gates many times through a user-defined number of layers, and then at the end we measure to get our queries or our set of or our configurations, which we call XQ over here. And we use those queries in order to minimize the cost function, which is in our case the negative log likelihood, which is equivalent to minimizing the KL divergence between the model distribution and the training distribution of our data. And by doing a feedback loop, we hope to learn the target distribution. So that's actually the question: can our QCBM, based on only some training samples, generalize to some new and good samples in order to learn the target distribution? So this is where this work came in order to assess the generalization metrics for any generative model on an equal footing. So the idea of this generalization metrics introduced in this work is to assess the generalization of any generative model only based on the queries they generate. So the upshot here is that this framework does not require the knowledge of the likelihoods or the probabilities. We only need to know what are the queries in order to know whether a model can generalize well or not. So one main pillar of this generalization framework defined in this paper is what's called the validity-based generalization, where we had a set of metrics, and we have this setup that's explained in this figure over here, where you can think of each data point as a configuration that is generated by some generative model of our interest, and we can classify them either through data points that are inside the training data or data points that are outside. So the ones that are outside correspond to this ensemble called GNU, and out of these we can define samples that satisfy a certain constraint. For instance, we could have configurations that have a fixed number of ones, or have an even number of ones, or odd number of ones. So those configurations belong to what's called a solution space, and those are the good or valid samples. And out of these, we define this set of unique solutions that are new and valid, and we call it small g sub. So out of this this definition, we can define the first, what's so-called the exploration, which is the ratio of the number of data points that are outside the training data over the total number of queries we generated. So basically, the larger this number is, the more our model is able to explore new data points. And the lower this number is, for instance, if it's closer to zero, then we expect our model to only provide us again with the training data. So the hope is that a good generative model will have a higher exploration. Now, another interesting metric that's defined in this framework is the so-called fidelity. That's not to confuse with the quantum fidelity. So the idea of this metric is to also assess how good the solutions that are generated with the generative model of our interest. So this is basically the ratio of the number of data points in this ensemble over the total number of new data points. So this tells us how probable a new data points is valid. And it's basically assess how good a generative model. So if a generative model is basically spitting out some noise, then the fidelity will be close to 0. But if it's learning the good target distribution, then the fidelity will be closer to 1. For the rates, it's very similar to the fidelity, but here on the denominator, we divide by the number of queries. So this quantity assesses the probability of a certain query that is generated by our model to be in this ensemble GSOL. And another interesting metric in this framework is the so-called coverage. So this is a different one compared to the fidelity and the rate, in the sense that it allows to quantify the diversity of solutions that we have in our set of queries. So basically, it's a ratio over the unique number of solutions, which is this small GSOL, over the total number of solutions that are not in the training data. So this is what this denominator means over here. So the larger this value of the coverage is, the more diversity of solutions, and the lower it is, the less diversity we have. So for instance, you can imagine that a generative model only spits out one single configuration every time you call for some configuration. You expect to get some very low value, but if you have a generative model that allows to provide different solutions, then you'll have a higher value of the coverage. And this is very desirable, for instance, in the context of some optimization problems where you want, for instance, in route scheduling, where you want to have different routes. And this will be helpful, for instance, in those kind of applications. Now, for testing these generalization metrics on our quantum circuit board machines, we use what's called the Cardinality dataset as a test bed, which corresponds to a set of bit strings with a constraint where a data point is inside the trained data, means that the number of ones in this bit string is fixed to this number k, and we fix this k in our experiments to the half the system size in such a way that the total number of possibilities is maximized. So k choose n is maximized when we have half of the system size, and the size of the training data is actually fine-tuned, so we can tune the size of the training data set using this factor epsilon. So the smaller this epsilon is, the less training data we have, and the larger it is. Basically, if epsilon is 1, then we are actually feeding all the possible valid solutions. But of course, this is not a good option because we're not leaving room for generalization. So a good rule of thumb is to choose an epsilon that's very small. And this is typically what we have in real-world applications. Now, for the training, we choose this uniform distribution where typically what we do in deep learning applications is that we assign a uniform probability to all the training data points. So this is basically equivalent to defining this training probability distribution, where if a bit string is inside the training data, then we're assigning this 1 over the cardinality of D train. And if a bit string is not in the train data, there we're assigning a 0 probability. And we're hoping that by minimizing the KL divergence between our model distribution and the train distribution, we aim to generalize and to get the target distribution, which is this uniform distribution over all bit strings inside the solution space, which is a much larger space than the training distribution if the epsilon is chosen to be small. So we did this experiment first for a QCBM with 12 qubits and with the line topology for different number of layers. So the cost function again is like, was the KL divergence between the P train and the probability distribution of the QCBM. So we were minimizing this cost function, but we also computed the KL divergence between the target distribution and the probability distribution of the QCBM. So here we chose epsilon to be 30%. So this means that we're taking 30% of all possible solutions. And we used a gradient-free optimizer. So that was the CMIS optimizer. And we also used the QLAC simulator, and we chose different seeds for the training in order to get to average our metrics. So as you can see in this plot, so we have the different types of KL as a function of the training step. So first thing we can notice is that for all types, for all different number of layers, and for both types of KLs, both KL train and KL target, we can see that with more training steps, both types of KL are decreasing. And the other interesting thing to note is that if we increase the number of layers, so as you can see for L equal to 4, from 2 to 16, we can see that both types of KL are also decreasing, which means that the number of layers is also helping to get better KL. And the striking observation that I want to focus on here is that if you compare the KL target, for instance, for 16 layers, which is this one over here, and if you compare it with that of the train, you can see that the KL of the target with respect to the target distribution is actually lower compared to that of the train distribution. So even though we're training with respect to the training distribution, we're actually learning the target distribution. So this is a very good signal that the QCBM is actually not overfitting to the training distribution, but actually learning the target distribution. And we can also see this for all the other number of layers. So for instance, for 8 layers, you can see also that that the target KL is lower than the train KL, and so on and so forth for the other types of, for the other number of layers. Now, if we include the framework of the generalization metrics I've explained in the past few slides, we can see a very similar picture. So here we added the fidelity, the coverage, the rates, and also the exploration as a function of the training steps, and also for different numbers of layers. So similar observation to the KL, we are seeing that we have an improvement with more training steps for both the fidelity and the rates, and also for the coverage. For the exploration, we're seeing a decline of the exploration, and that's something we expect, because the more we're learning, the more we're actually less exploring the search space. And the other interesting thing to note is that if we include a random baseline, if we have a model that just spits out random configurations, we're getting these values for the fidelity and the rates, and we're actually finding that the QCBM does better than, even with 2 layers, does better than a random baseline. So this baseline is just to show you that we're actually not spitting out random configurations, but actually doing something better. And similarly to the picture we have for the KL, the more layers we have, the better the generalization. And if we also look at the picture of the coverage, which again, as I've mentioned earlier, quantifies the diversity of solutions, we can see that even though the QCBM is actually generalizing better than the random baseline, it still keep maintaining a good level of diversity as good as the random baseline. So we're not actually sacrificing the diversity, even though that we're generalizing to good samples. So this was a brief summary of the first pillar of the generalization metrics presented in this paper. Now, I wanted also to focus on another pillar that we focused on more on the race that we established between classical and quantum generative models. So this pillar is called the quality-based generalization, where the idea is that given a set of valid and new samples that we called earlier as GSOL, what we want is to assess the quality of those solutions. And this can be done through the proxy of some cost function that can be defined based on the context. So for instance, you can define this cost function as, for instance, the cost of design of assessing the quality of some drug or some molecule or something like that. So you can see that this cost function can vary from one real-world scenario to another. And one quantity, the first quantity that we can define here is the so-called minimum value, where what we can do is we can take the minimum bit string that minimizes the cost in this ensemble over here. And so you expect that the lower this value is, the more our generative model is able to provide us with high quality solutions. But now the thing is that you might think that, well, if we take the minimum, we might have the chance, we might just get this result by chance. So what we do is we introduce some kind of averaging, where instead of taking the minimum, what we do is we take an average over the five lowest percent costs inside our ensemble GSOL. So this allows us to avoid the chance of getting a minimum, avoid the issue of getting a minimum just by chance. And the last quantity that we define in this quality based generalization framework is the so-called quality coverage, which quantifies the diversity of high quality solutions that were not seen in the training data. And it's basically defined as follows. So what we do is we count the number of unique solutions that have a cost that's lower than what was seen in the training data. So for instance, let's imagine that you have a set of molecules in your training data set that have a certain cost or a certain effectiveness. Let's say you have a cost -7, and let's say your generative models allows you to get new samples that have a cost -8 or -9. Then those samples that have -9 and -8 are actually samples that are included in this formula over here. And that's what's in, basically this is what the purpose of this quantity is, to quantify the number of those solutions that were not included in the training data. Now, for assessing this framework and using the QCBM, we use another data set that's called the evens training distribution, where given a set where a bit string is included in the training data set, if it has this constraint where we have an even number of ones, this means that the size of the solution space will be 2 to the n minus 1, where n is the system size. And again, similarly to the cardinality distribution, we're tuning the size of the training data using this epsilon. So for the task I'm going to talk about here, we're choosing epsilon equal to 0.9 and the system size, again, to 12 qubits. And for the choice of the cost function that's used in order to differentiate between different samples, we choose as a test bed the negative separation costs, which is simply defined as the negative largest distance between two ones in a certain bit string. So let's take this example over here. So if you look at this bit string, you have these two ones. The distance between them is 2. But if you look at these two, they're actually further apart. So the distance is 1, 2, 3, 4, 5. So we're actually going to count this distance, and we're going to assign the cost over here to -5. Now, if you look at this bit string, it's all ones. So the distance between two ones is always 1. So we're going to assign the negative of that. So that's -1. In this bit string, we only have one in this bit string. So by definition, we set this cost to 0. So that was for the definition of the cost that we use for assessing the quality of the generalization. Now, in order to encourage our generative models to generalize to those samples that have a lower cost, what we do is we introduce this trick that's called the softmax reweighting, where instead of assigning a uniform weight to each training data points, what we do is we're actually reweighting the probability, so in such a way that samples that have a lower cost will have a higher probability. And this is done through this softmax reweighting, through introducing some artificial inverse temperature beta. So the idea is that if we have some non-zero temperature, then samples that have a lower cost will have a higher probability. And the idea of this trick is to encourage the model to give more importance to samples that have a lower cost. And we have tried this for QCBM with 12 qubits. And when we train using a uniform train distribution, this means with beta equal to 0, or using an infinite temperature. So in this case, the train distribution looked like something like this, as you can see in this green histogram. Now, if we generate samples from the trained QCBM, we get something like that, where you can see over here the lowest cost in the trained data is -7. And you can see over here, the QCBM can still generalize to some samples that are lower than -7, but that's not that good. So the idea was to use a temperature that's non-infinite. So here we use a non-zero temperature in such a way that this beta is a finite value and it's not 0. By doing this, you can see that the train distribution is shifting, and we're giving more importance to samples that have lower costs. And you can see the effect of this. For instance, if you look at the height of this bar for the -7 compared to this one, we can see that the QCBM kind of starts to feel the bias in the training distribution. But this is not prominent if you look at the probabilities of those samples over here. So what we did is to lower the temperature by a factor of half, which is equivalent to multiplying the beta by a factor of 2. So this even biases the training distribution more toward costs that have a low toward samples that have training samples that have a lower cost. So you can see that in this case, the QCBM starts to feel much more the bias in the training distribution and increases the probabilities of those samples that were not seen in the trained data. And this can be computed through this probability factor and also through the utility. So if you look at the utility that we defined earlier, it's -8.89, but for the others, it doesn't even go lower than -7. So just by introducing this trick of softmax reweighting, we can encourage our models as you can see over here for the QCBM, we encourage the QCBM to generate samples that were not seen in the trained data, and we encourage to give more samples that have a lower cost. And to convince you that this is not that the QCBM is not doing something random, we sampled 10K configurations from a uniform distribution, and out of these samples, we computed this histogram, and we can see over here that the QCBM for this temperature for this inverse temperature is actually more biased toward negative cost compared to this one. So this is like a proof of concept that a QCBM can generalize both in terms of providing good and valid solutions, and also in terms of providing high quality solutions, as we highlighted in this example. Now, before going to how to the second part where we're going to establish a race between classical and quantum generative models, I would like to open the floor if there are any questions regarding the first part of how we can define of how quantum circuit-borne machines are generalizing. Are there any questions so far?
Yeah, like if you have any question, like please unmute yourself and ask.
Sure.
Seems not. Yeah.
So far, so good? Okay. Yeah, if there are no other questions, then yeah, let me now shift our focus to the race that we established between quantum and classical generative models as a way to search for a practical quantum advantage. So as I motivated earlier, this is kind of a race between quantum models and classical models. So for the race, as I've told you earlier, we will have different types of tracks. So in our experiments, we designed two types of tracks. So the first track was to fix the budget of the number of queries that's retrieved from each generative model. So this is motivated from the fact that sometimes getting samples is actually expensive, so we have to set a budget for that. So for instance, some quantum devices have a very high cost for sampling. So in these cases, it's good to fix a budget for the number of samples. For the second track, we're now fixing the number of cost functions evaluations. So this means that in some cases, evaluating a certain cost function is very costly. So you can imagine yourself in a setting of a laboratory where doing an experiments can have a very expensive cost. So for instance, doing a clinical trial can be expensive. So there we need to set up a budget for maybe doing some critical trial that will provide us with some cost for a certain drug or a certain catalyst. So in these cases, these kind of situations allow us to motivate this second track. So these are just two examples for tracks that we can imagine, but you can also think about other tracks. So these are just for the purpose of illustrating this race analogy where we could have different tracks in a race between classical and quantum generative models. Now, so this was the race tracks. Now, we also, in order to have race, we need the racers. So we have the quantum models and the classical models. So for the classical models, we use fine-tuned classical generative models. So we use the recurrent neural network, we use the transformers in natural language processing. So we also use the variational autoencoders and also the WGANs. And on the quantum side, we use the fine-tuned quantum circuit-borne machines. So of course, those are the models that were available to us and that we use for the comparison. But of course, nothing forbids us from adding more runners. So of course, if you're interested, you can add your top runners to this list and do more and add more and do more benchmarks. So for the training and the assessment of the generalization, we choose now, instead of using only 20 variables or 12 qubits for the quantum model, now we use 20 variables, and we set and we also use the evens data distribution that I've introduced earlier, and we fix the number of the data portion epsilon to two different values. So we choose epsilon 10 to the minus 2. That give us a size of a training data that's roughly equal to 5,000. And we also use we decrease the epsilon with 1 order of magnitude, and that provides us with a size of the training data that's about 500. So this corresponds to the low data regime, and this is like another regime of. So this was just to show you how the different models behave at different sizes of the training data. Now, after choosing our runners, we select the different tracks, we train and fine-tune for a fixed number of training epochs and also for a fixed number of training seeds to average our results. So for the first track, we fixed the number of sampling budget to 10 to the 4, and for the number of cost function evaluations or the number for unique samples to 10 to the 2 for the second track. And after doing this, we evaluate the generalization metrics, and this will help us to identify the winners in each race. So we did this for the first epsilon, which is 10 to the minus 2, which is again about 5K data points. So here what we plotted is the quality coverage, which for both track 1 and track 2 is a function of the training step. So just as a reminder, the quality coverage was the quantity that allows to quantify the diversity of solutions, of unique solutions that have a cost that's lower than what we have seen in the training data. So what you can see is that with more training steps, you can see that the QCBM and the VAE and the WGAN are doing great. So they're increasing and saturating, but for the transformer, it's actually, and for the RNN, we're actually getting a drop of performances. And we can see that the QCBM is competitive with the VAE and the WGAN on the track 1. But if we go to the second track, now we're getting something different. Now we can see that the VAE and the WGAN is better than the QCBM, but still the QCBM is better than the transformer and the VAE, okay? So QCBM is still doing good, but not that good if you look at the track 2. Now, the interesting thing happened when we decreased the size of the training data. So this is when we went to about 500 data points. So this is the scarce data regime. So when we computed the quality coverage for both track 1 and track 2, you can see that the QCBM has the largest quality coverage at the end of the training compared to the other generative models. And this is also the case for the second track compared to the other generative models. So this showcased that the QCBM has the largest diversity of high quality solutions compared to the other generative models. It's interesting to see that as well if you look at this picture by picking up the highest value throughout the training steps. So just to simplify the visualization, so we can see that the QCBM here is competitive with the RNN. You can see it from this point here where we have the QCBM is competitive with the RNN. And if we compare the quality coverage for the generative models on the track 2, we can see that QCBM has the highest value. So again, this showcases the effectiveness of the RNN, of the QCBM in the scarce data regime compared to the other generative models. And this picture is further reinforced if we plot the utility, which is again, as I mentioned earlier, the average over the 5% solutions that are the lowest cost 5% solutions in this ensemble G. So you can see for track 1, the QCBM has the lowest utility, meaning that we actually getting a cost, an average cost that's lower compared to those found by the other generative models. And we can see that for track 2, the utility found by the QCBM is about the same found by the VAE and also better compared to the other generative models. So this again, this picture also highlights the effectiveness of the QCBM in the scarce data regime. Now the question is, did we find practical quantum advantage? Well, the thing that we highlighted in the paper is that we actually found not exactly practical quantum advantage, but actually a potential practical quantum advantage, which we denote as PPQA, which we define as achieve an advantage of a quantum generative model with respect to the best available classical generative models using our best efforts that were available to us when we were conducting the research. So of course, some other people will come after us and test this and add their own benchmarks, and the results might change. So in this case, what we hope for the future is to establish more races and more benchmarks by including other generative models and more powerful classical models and also more powerful quantum models in order to establish what's called a robust practical quantum advantage, where we hope to establish an advantage with respect to the best classical generative models. So this will be the definition of a robust practical quantum advantage. And this will come if there will be more benchmarks in the future and more work and more races between quantum and classical generative models. And I would like also to note that this potential practical quantum advantage is actually much better compared to what we call in our paper the limited practical quantum advantage, which is basically comparing a classical algorithm with its quantum counterpart. So for instance, comparing a classical restricted Boltzmann machine with a quantum restricted Boltzmann machine, or comparing a classical annealer with a quantum annealer. So this kind of comparisons lie in the definition of the limited practical quantum advantage, but actually we're doing better by comparing different kinds of generative models. So the hope, as mentioned earlier, is to arrive at this robust practical quantum advantage. So this brings me to the conclusion, where I hope I've convinced you that quantum circuit-borne machines can generalize. And in this presentation, we have also provided a definition for practical quantum advantage raised in the camp of generative modeling. We have also proposed the first race, or the first comparison in terms of generalization between classical and fully quantum generative models. And we have, most importantly, the main message was that we have demonstrated the efficiency of these quantum circuit-borne machines in the scarce data regime, as opposed to the classical generative models, which are known in the literature to be data hungry. So this brings me to the end of this presentation. I would like to thank you all for your attention, and I look forward to questions. Thank you so much.
Yeah, thanks, Mohamed. So is there any question from the audience?
Hello?
Yeah.
Okay, I've got a question. So if I follow correctly, the simulations you did were all for relatively small quantum circuits. Do you have any thoughts on how well a quantum circuit-borne machine will scale, say, in the supremacy regime where you can't measure the full probability distribution?
That's a great question. So again, just as a reminder to the audience, to the system size that we chose in our study. So we chose 20 qubits for the QCBM and also 20 variables for the other classical models. So of course, that's a relatively small system size compared to the supremacy size that you mentioned. So the goal of these experiments was just to show, just a first step toward establishing a practical quantum advantage. Of course, there's much more work to be done toward scaling this up to larger system sizes. So of course, one of the things that we need to figure out is how we can train the QCBMs, not using the k-elder versions, but actually using cost functions that are based only on the samples that we get, because in these scales, we don't know how to figure out what's the probability of a certain sample. So of course, there are a lot of challenges, but the main hope of our work was to provide a concrete and a quantifiable framework for comparing classical and quantum generative models while waiting to figure out how we can scale this approach to larger system sizes. So that was the main contribution. So of course, like to answer your question, like I don't know how this can be scaled. So of course, a lot of research needs to be done in order to see how the training can scale to much larger system sizes. So one way this can be done could be through the use of quantum-inspired algorithms, either using tensor networks, where we can use these architectures in order to see how maybe quantum circuits can perform at the scale of large number of qubits. This can be one way to scale it up while waiting for the next generation of fault-tolerant quantum computers. I hope that answers some part of your questions, but it's a very good one.
Thanks. Yeah. Yeah. I wonder whether, like, say, the cross-entropy benchmarking could be used.
Absolutely, yeah. So that's absolutely, like the cross-entropy benchmarks is based only on the samples, so that would be also an interesting benchmark. Just maybe one thing to note, like the cross-entropy, I'm not sure how we can include the quality generalization part in the cross-entropy. So maybe it's something to think about.
Thanks.
Yeah, thank you.
Okay. Are there any further questions? Seems there are no more questions. So thanks, Mohamed, for joining, giving this talk. And we have almost every week we have these talks, and these are online. So feel free to attend and all. And all the recordings are posted. So yeah, thanks again for agreeing to talk.
Wonderful. Thank you so much for having me. It was an amazing experience, and yeah, it's a great pleasure.